Hey everyone, welcome to this stream. Let's see what we have to do today. Right, arithmetic. Right label, right go to, right a, right function, right return. Okay, today we have to implement right call. Okay, then let's get started. Right call. Wait, these are the steps we have to carry out. Didn't we already wrote the code for this? What the heck? Wait. Return address, LCL. No, we didn't. We started writing it, but we didn't actually code it up. So that's what we are going to do. So we'll start from, let's see. We'll start from here. Calls a function informing that an args argument have been pushed. The syntax of call will look something like this. It will start with call, then function name and number of args. This is this variable specifies how many arguments we have to pass to this function. All right, so first of all, when we encounter a call instruction, this is what we have to do inside the assembly code. Push the return address label using a translator. Return address label. And what is this return address anyway? This return address, I think it is the address of the next instruction. Let me first delete this. Return address label. Oh wait, push the return address label. I see. This label, they're talking about this label. Wait, this label. So we have to first add a label. Should we edit first? No, before we add this label, we first have to implement all of the steps. So before we add this label, we have to push this return address label. But what are we going to call this label? Return address label. We can call it just a return address label. We have to provide a variable as well, because we can call a multiple functions inside a single assembly file. Therefore we'll have to keep track of which function, which label belongs to which function call exactly. So for that, let's see, code writer, what the hell? We'll have to get a variable. Should we call this variable? So let's call it call ecount. Right. We'll have to push that address. So to push an address on the top of the stack, first we'll have to get that label. How do we push a label on top of the Can we do this at then red ADTR label and call e count. First we'll select this and let's see, we'll store this. Can we do this? Should I write d is equal to m or d is equal to a over here? What will be a in this case? So this return address label is just a symbol which contains the line number. Right. So a will be the line number. Yeah, we should write d is equal to a. Now we need to select this. We need to push this on top of the stack. So first we'll select the stack pointer and m is equal to d. Right. Wait, first we'll have to dereference. Then after this we can do m equal to d. Yeah. After that we again need to get the stack pointer and increment it. Okay, this is it for push return address label. Now we need to take care of push LCL. So to push LCL, we'll have to select this LCL Okay, where was I? Push LCL. Now this will select LCL. Do I have to store the value which is stored by this LCL? Yeah, I think so. We have to store the value. Therefore, we'll have to do d is equal to m. Because m contains the value. Now, again, we can select the stack pointer. We'll have to do a is equal to m and m equal to p. After that, again, we'll have to get the stack pointer and increment it by 1. We'll have to do this number of times. So let's copy this. In this case, instead of LCL, we will select arc. Let's copy it again here as well. We should select this. Here should be that. And finally, no, we are done with pushing the values. We have pushed return address, then LCL, arg, this and that. Now we need to change the argument pointer to this. So for that, we'll have to get this an args variable, subtract it from sp minus 5. Okay, let's see how we have to get this. What can we do? We'll have to use a variable, temporary variable, to keep track of this address. Yeah, let's get a variable. Let's just get 5 and we store it inside data register. Now we'll get a temporary variable. Let's call it address arg. It doesn't matter whatever we call it. Now yeah, let's store the m is equal to d. So now this address variable will have 5. Now let's get stack pointer. We'll have to get the value of stack pointer. So for that, we can do d is equal to m. because m contains the set pointer value, right? Yeah, it does. Now we can again select this addr arg. Let's just call it addr because it takes a lot of time to write it up. Now we can do m equal to d contains stack pointer minus m, so this will do sp minus 5. Now we need to get this args variable, so we can do at the rate and arg, and args variable is in arg2, and we'll store its value inside a data register. This should be a. Now we can do the same steps. First select the address variable, then we can do m is equal to d. Wait, this time instead of m is equal to d minus m, we have to do m is equal to m minus d. So this will give us the value. Now all we need to do is let's store this value inside a data register. Now we need to change the argument pointer. So first let's select the argument, and we can do now m is equal to d. So now this argument variable pointer is changed to sp minus 5 minus n args. After that we have to change lcl pointer as well. Okay, it will be easy. The only thing we have to do is get the stack pointer and store its value inside a data register, and now we can select lcl, do m is equal to d. Cool. So now the value of lcl pointer is also changed to sp. Now we need, oh wait, let me give space somewhere. All of these instructions were for arg is equal to sp minus 5, right? Sp minus 5 minus n args. Up to this point. These are the steps for LCL is equal to SP. Now we have to figure out the steps for go to function name. What is this function name? Oh yeah, it is in argument 1. So we have to jump to that function name. Well, we can do at then arg1. Let's select this, and we have to jump to this function and conditional. So we'll use 0 and jump. Wait. Okay, correct now. And after that we need to write this return address label that we pushed onto the stack earlier. So can do this return address label call e count. Okay, I think this is it for the call instructions. This seems all right. So let's copy this code. First uncomment this code. Okay, password dot type equal to call. This is correct. We also need to get argument 2. So let's get it. Call C. Wait, am I missing something? Why is this just sp m minus m equal to m minus 1? Oh, wait. Let me check other function. This is for return, and these are the steps for function, right? Yeah, it is correct. So the steps which are already in the call, the right call method, are this one. So I basically just copied this method. So yeah, it's all right. Let's see. I need to copy this. Paste it over here. Let's get rid of this empty lines. New line. This is not what I actually wanted. It's all right. I don't think we need to change anything else. Just this one. So to change call ec count itself dot call ec count. Now after we are done writing, we need to do something else. We need to increment this call ec count. This should be call C. Okay, what else do we need to do? I think that is it. That was it. So we have implemented call. Apparently we have implemented all the instruction sets. So let's try to get a translated program now. VM translator, and now we'll try to test this program. Nested code. Wait, but did we write this? Oh wait, I forgot about this init. Not this one. Where is it? Right, init. Yeah, I still need to write this function, this method, write init. What does it contain? Write init. Let's see. Yeah, this bootstrap code. We still need to implement this bootstrap code. So to first we have to change the value of stack pointer, or I should say initialize the value of stack pointer. So we get 256, store it inside a data register, then we select this R0, which is pointing to the stack pointer. Oh wait, we don't need to select R0, we can directly select the stack pointer. And then after that we can do m is equal to d. This will initialize the stack pointer. After that we need to call sysinit. So to call sys.init, wait, there's no, wait. In this syntax of call we don't have any argument. It should be at least 0. Wait, suppose if we don't have any arguments for this call, does it change our function? Right, call. What if we pass nothing inside this number of args? what will happen then? It will be just none, right? We are using it over here, arg2. Yes. In this case, it should be 0. So we'll have to provide a condition over here. What can we do? Let's see. If parser.arg2 not equal to none, then we assign its value. But if it is equal to none, then we have to pass arg2 equal to 0. Yeah, this will work. This will work for sysinit as well. So now let's write the sysinit. What do we need to do here? We need to write the code for calling. So should we just call that method instead of writing the code again? I think so. So what if I do first? Let's do parser and we don't need to provide any condition, but we do need to write init c. For now it will have this code. Right, and okay. init code. Init C. But we are not going to do this first. We have to call the dot write call, but we'll have to pass the parser. Okay, it doesn't matter. Let's get a parser and we'll pass call this init. This is what we have to pass to a parser, right? Yeah, we have to pass the instruction. And after that, we'll pass this parser to write call. Let's check if this works or not. Still need to change the main method, main setup, because we still haven't wrote the condition for call C call. In this case, should call write call. Wait, there's still one more thing remaining to do. We need to call this init. Yeah, we are already calling it over here. Self init, right init. Okay, so this will take care of it. Let me write this call sys. I hope this will produce right code. Let's see. Will this work? Which program? Let's first translate this Fibonacci element. Function calls. Function calls Fibonacci element. Yeah, let's just give this. It should give us Fibonacci element dot asm. Oops. What happened? Yeah, I see. So it is complaining about this instruction call. It doesn't matter. Let me just pass 0. This will work now. Yeah, it gave us the correct output. We have the Fibonacci element.asm file now. Let's open it up. Function call Fibonacci elements ASM, and let's open the CPU emulator. Function calls in Fibonacci element.txt. No animation fast. We have an error, guys. This is the output and this is the comparison file. That means we are messing up somewhere. Before we do anything else, let's open the VM emulator and tools. VM test script. This will give us an idea how this function or this program is working. So let's load the program. Setup SP. First push constant 4, then call main dot Fibonacci 1. A lot of things happen. So push argument 0, then push constant 2. We'll check for less than condition, and if it is true we should go to main Fibonacci. Wait, there's a lot going on. You know what, instead of running this, let's check this code. So this is a problem. Suppose we go on with this init code. Then we write the code for call sysinit. This will perform the necessary steps, and after that it should jump to sysinit. That means it should jump over here. Let's try to walk through this program step by step. First we'll fire up CPU emulator. Let me minimize this VM emulator. Let's clear the RAM. Program flow script. So let's see. When we do one step, now we need to get to 56 and change the stack pointer. We have to 56 here. Now we'll get the return address label stored inside data register 60. We'll get the stack pointer A is equal to M is equal to D. We'll store that address on the top of the stack. For that we'll increment the stack pointer. Okay, now we'll get the LCL and store its value inside data. LCL is right now 0, and we'll push this value on the top of the stack. We increment the stack again. Now we'll get arg, it is again 0. Push on the top of the stack, increment the stack pointer to 59. Now we'll push this value. So at 3, select at 3, we'll push that value on the top of the stack, and then we increment the stack pointer. Now we'll get that value, that pointer value, and we'll push its value on the top of the stack, and we'll increment the stack pointer. So now the stack pointer is pointing at 261. After that, this and that, what else do we do? Now we'll do this, change the argument variables value. So first we store 5, then store its value inside data register. Now we get at 16, this is a variable, store that value there. Now select the stack pointer, get its value inside data register. Okay, I will do M is equal to D minus M. So the value of this variable will be 256 minus 5, 261 minus 5, so it is 256. Now we'll get this 0, so this one is inside data register. Now we'll do M is equal to M minus D. The value of address remains the same. Now we store its value inside data register. We have 256 over here, and we select the argument pointer, and change its value to 256. arg is now pointing at 256. Okay, what do we do after that? Where is it? Arg. Now we get the stack pointer and get its value inside D. 261. We change the LCL pointer's value as well. It should be 261 as well. Okay, now we are going to jump at sysinit. So we get sysinit. We will jump at 60. So we didn't actually need it to jump because it was just after this instructions anyway. So now we'll start with the actual program. So sysinit. Inside sysinit we first get 0, store its value. Inside data register we get 17, which is a variable. We will get I variable, store the 0 inside it. Okay. Now what do? We get this func.stop 0. Wait. Yeah, right. We again select I, store its value inside data register. It is 0 again. We select at 77 and D jump if equal to. So it is equal to 0. So we'll jump at func stop 0. Right. So we jumped at this position. So what really happened is this loop should run the number of times we have local variables, but in this case, in case of sysinit function, we didn't have any local variables, so we didn't jump. Let's go to this address 261. This is the working stack right now. 256 was the base address. And we are at 261. 1, 2, 3, 4, 8. 1, 2, 3, 4, 5. What is this 60 again? Yeah, it is the return address. And this is arg, I think. Is it arg or yeah, arg? Then which 4 variables we have? Arg, local. No, it's not local. Yeah, it doesn't matter. So now we push constant 4 on the top of the stack. And then we increment the stack pointer. Now we'll call this main.fibonacci. So that's a lot of code. First, we'll select the return address label at 4140 and store its value inside the data register. Let's go to 140. 140. This should be the label address. Why? Wait, we are assigning an incorrect return address label. I see. It's because these labels are at same position. The values of both of these labels is 140. I see now. Okay, it is correct. So WebOP, we selected 140 and stored it inside data register. Now we select the stack pointer. Okay, what are we going to do? M is equal to D. We are changing the stack pointer's value. Okay, why are we doing that? First we select stack pointer. A is equal to M equal to D. D is 140. Okay, this seems incorrect to me. Why are we changing the value of stack pointer again? Let me check the slides. Oh no. Here we're getting the return address and pushing it on top of the stack. Okay, I see. Yeah, it is correct. We're just pushing the value on top of the stack. Not this one, this one. We will be pushing this 140 value on the top of the stack. Okay, so I did it. Now we are going to increment the stack pointer. We did it. Now we have to change the value of local. It should be D equal to M. First get its value and store it on the top of the stack. Right, We get the value of arg. Store it on the top of the stack. Now we'll get the value of this. After that, we have got the value of this. Now we'll get the value of that. Now after that, we are going to change the value of argument pointer. So first we get 5 inside data register. Now we get at 16 m is equal to d. We store 5 there. We select stack pointer and get its value. We change the value of ADDR to d minus 267 minus 5. This is 262. Now we get 1, which is the local, I guess. I think it is the local pointer. No, it's just one for one argument. So we'll do m is equal to m minus t. So the value of, now we get this value inside d, and we select 2, which is the argument pointer, and store this value there to 61. Now we select the stack pointer again, store this value inside data register, and after that, wait, why are we storing the stack pointer's value at LCL? Yeah, changing the value of LCL. Now we will jump to main.Fibonacci, which is at, in this case it should be at 142, which is correct. We will unconditionally jump there. Okay, we are here inside main Fibonacci function now. Let's see what happens here. First we select 0 and store it inside data register. Now we select I, change its value to 0. Now, oh yeah, this is for assigning local variables, but in this case we are not passing any variables, so it will be just 0. If it is 0, we are going to jump at 159, which is this step, push argument. And we did jump, so now we'll push argument 0. We store 4, we push 4. big program. I think I'm going to skip all of these steps because they are not that necessary. So where were we? I forgot. Wait, this is a recursive program. We can't step through the program. It will be rather confusing. We can't keep track of all the variables in our mind. Or we'll be calling this main.Fibonacci again and again. I can't do it. Let's just walk through it. Doesn't matter. We were at this step at SP. So far it seems correct. Now we push constant 2. Now we check for this condition less than. Condition was 0. That means it's what false. 4 was not less than 2. So therefore we stored 0 on the top of the stack. Now we need to increment the stack. I will check for if go to if true. What? If go to true. So we'll decrement the stack pointer, get its value inside data. It is 0. If it is jump if not equal to 0, JNE. Jump to if true if not equal to 0. Wait. Yeah. It is false, therefore we are not jumping. Jumping to if true, so we'll jump to if false. So we'll unconditionally jump to if false again, which is where 302. Where is if false? At 302. Okay, where is it? Okay, over here. We should jump at this point. Let's see if we jump at that point or not. Yeah, we did jump, but is it at this point? Yeah. So now we are going to push 0, argument 0. F2 is equal to d plus m. Wait, what happened? I lost track of the code. First we selected 0, stored it inside data register. Now we selected variable and change its value to 0. After that we selected 261 plus 0. So yeah, that's correct. Now we'll store the value pointed by this inside D. It is 4. Argument 4. Argument 0 is 4. We'll push this value on the top of the stack. Yeah, we do that. After that we'll push constant 2. Now we'll subtract 4 minus 2. So we should have 2 on the top of the stack. Okay, it happened. Now we are at this point. Call Fibonacci 1. It's a recursive step. And in this case we have return address label 2. So you see how convoluted this is. I will be right back, guys. We are at this point. Should we go on with it? Okay, let's walk through it. It doesn't matter. So we'll store this value on the top of the stack. 390. What is that? 390. It is this point, I guess. Yeah, it is. So let's do that. We won't know if this is correct or not. Let me translate that other program. What was it called? Simple function. Simple function dot vm. Simple function dot asm. Here we first have the init code. Here we have a problem because in this case we don't have the init code. Therefore we can't call sysinit. We don't have sysinit in this case. So this whole program is incorrect. Let's get another static test. Let's get the nested call. Nested call. Nested call. We have the nested call.asm. Let's try to run this program and see if it works. Function call, nested call.tst. No animation fast. Run it. Nope. We have an error here as well. All the values are different. So, and we can't even go through the program step by step. The only thing we can do is check our implementation in this code is correct or not. So we'll have to check if we wrote correct instruction for call or not. So let's see. Get the return address, push it on the top of the stack. We get the LCL, push it on top of stack. We get arg, same thing, this, that, and after that we get sp minus 5 and arg. So let's check if this is correct or not. First we get 5 stored inside data register. Then we get address variable, we store 5 there. We get a stack pointer again, store its value inside d, then we do d minus n, so we'll have sp minus 5 inside this address variable. Now we get arg2, d is equal to a, address is equal to m, which contains sp minus 5 already, so we do m minus n args, and now we have to store this value, so we get it inside d, and we change the argument pointer, and it's equal to t. It seems correct. Now for LCL is equal to sp, first we get the stack pointer value, store it inside data register. Now we get LCL, change its value with d. This is correct. After that we have to go to function name, so we get argument 1 and we jump there and conditional. It seems correct. After that we have return address label, call it count. This is correct as well. So I don't find any problem with call instructions. Let's check function instructions, I guess. repeat n more times, push 0. Okay, that was it for function. So first we get function name from argv1 and get the label. After that we get argument to store its value inside data register. D is equal to A. Now we get I, M is equal to D. We store the argument 2's value inside I. We get I again, store its value inside D. We check for this condition. If it is equal to 0, we jump to this point, stop. But if it is not equal to 0, we get stack pointer, get its value, get the top, no, we change the top value of the stack with 0 and we increment the stack pointer. After that we decrement I and we jump back to this condition. So let's walk through this function. I think we did it pretty much well yesterday. We don't need to go through it. That was it for function. Now let's check return. Here we first get the local pointer value and change and frame variable with that value. M is equal to T. After that we get Y, we store it inside data register. We select the address variable, we change its value with 5, we select the end frame again, we get its value inside data register. Now we select address variable, we do M is equal to D is M frame minus M. Now we do A is equal to M and D is equal to M. Store its value inside return address. This seems correct. After that we have to pop the value from the stack. So we decrement stack pointer, get its value, A is equal to M, D equal to M, argument A is equal to M equal to D. Now we have to do SP is equal to R plus 1. So for that, so let's see, D is equal to A plus 1. Is this correct? Yeah, this is correct. Now we get the end frame. Show its value inside data register. We get address variable. M is equal to D and frame -1. A is equal to M. D is equal to M. To A. Address M is equal to D and frame D is equal to M. D minus M and frame minus address variable. A is equal to M, D is equal to M. This is equal to D for 3, 4, and finally we have return address. At return address jump. Wait. So at return address is a variable. It contains the return address. Let me check. Where is it? Its return address is equal to M is equal to D. So this variable contains the return address M equal to D. But what are we doing over here? We are selecting at return address, but this return address is just the variable 16. What if it is something like this? At return address is equal to M. Maybe this is what we have to do. Right. So let's try to do this and see if it works or not. What do we need to change? We just need to add A equal to M, right? Let's see if this works or not. Let's load the instruction. Wait, we have reduced the amount of incorrect values. So this is good, this is good. But what is incorrect? 261, 261, 256, 4000, 5000, 135, 246. 261, 267, 256, 4000, 5000, 123, 246. The value of RAM5 is incorrect. Everything else is correct. This is RAM5. It should be 135. Let's see. This is the stack pointer. Then argument, local, this and that. Then what is this? Do we need to change anything else? Let's try to translate different program. This time let's translate Fibonacci element again. The script of Fibonacci element. Oh, great. Fibonacci element is working. Awesome. So that means we are getting problem. We're getting error in the nested call only. Let's try to test it for statics test. Statics test. Let's load the test script of statistics. Fibonacci statics test. Okay. The output of RAM 261 is incorrect. It is 8 while it should be -2. It's a 1000 lines program. We can't walk through it step by step. What about this simple function? It's not going to work, I know, but let's just try to compile it. Let's load it up. Yeah, it didn't work. But wait, you know what? Let's see, while compiling this, let's not write in it. So let me comment out this code for now. How do I get out of this? WQ. So now let's try to compile it for the simple function. In this case, yeah, let's try to load it now. Yeah, as I suspected, the written instructions were incorrect. So that's why it was not giving us correct output yesterday. So we can say that the instruction for return are correct, return and function. So my guess is we have incorrect instructions inside. So let's uncomment this line now. Let's check right call. This function must contain the bug. But where is it? Surely this function should contain the bug. This is the documentation of that nested call program. We are getting incorrect results for this function only. Nested call. Let's load it again. Function calls, nested call, tst. Right. This function is giving us incorrect results. Let's compare the stack. Yeah, only one value is incorrect. Nested call is an intermediate case in terms of complexity intended to be used between simple function and Fibonacci test. It may be useful when simple function passes but Fibonacci element fails or crashes. Several requirements of function calling protocol that are not verified by the other test can be used with or without the VM bootstrap code. It runs the same test on the VM emulator. Is implemented entirely within the system file. The first function in the system is sysinit. This allows it to be used before the bootstrap code has been added to the VM translator, since there will be no file process. Let's initialize this pointers. If RAM file is incorrect, there may be a problem with setting up the arg pointer. Okay. So they're saying there will be a problem with arg pointer. We'll have to check where are we setting the arg pointer. We are setting the arg pointer inside return. As well as inside the call. So we are setting arg pointer inside return instructions like this. But this seems correct. Or maybe this operation is incorrect. So let's review it. What are we doing over here? First we select the arg pointer. Oh wait. Yeah, this is for call. Let's check return. Is this because of this line of code? Let me try to write it like this. I'll first get the arg pointer. Wait, this is for return, right? Where did I? So here we're changing the stack pointer value, so don't need to do this. But we are changing argument over here. What do we do over here? First we get the stack pointer, decrement it. Yeah, we do need to decrement the stack pointer. So for that we can do, first we have to select the stack pointer when we do m is equal to m minus 1. Now a is equal to m and d is equal to m. Yeah, this seems correct. After that we select the argument pointer. We do a is equal to m and equal to t. Is this correct? If argument is pointing at correct location, just this one, then it should have the value then. But if there were no arguments for that particular function, then it will just overwrite this return address, right? So let's check function now. Nothing interesting happening over here. Where is call? Here we are changing this argument value. So let's go back to call now. Arg is equal to sp minus phi minus n args. Let's review it again. First we get phi, store it inside data register. Then we get address variable. We change its value with this d. Now this address has phi. Now we get the stack pointer. Get its value inside data. M contains stack pointer value. Then we do m is equal to p minus m. So it will be sp minus phi. This seems correct. Wait, yeah, here, right. This is incorrect as well. Instead of b is equal to a, wait, this will be replaced by, as this is not a variable, it is a label. Yeah, it seems correct. There has to be a problem with this arc variable only. Is it because of this init code? Is it? Temp variable is incorrect in our case. This is the state of our RAM, and this is the incorrect state. Each and every value is correct, but just this temp 0 is incorrect. What about this 266? This seems incorrect. Let's check the stack. 261. Is almost similar, but these values are different. To 76 to 77. Calls is add 12, 123 and stores return value 135 in temp 0. This is what is causing the problem in our case. Temp 0, we don't have temp 0 as 135. We have 123. Where is this line? This is main. That is over here. Let's check the code. No problem. This line of code pop temp 0. That is correct. First we are getting 0, storing inside data, address variable 0, get 5 is equal to a. Wait. Yeah, this is correct. Address is equal to m is equal to m plus d. Address contains 0 again. 0 plus 5. Is correct. Pop temp 0. Let me check. It can't be incorrect because I have already tested these programs. Okay, this is the source code for push and pop temp. Oh wait, wait. This is also the location where the argument is initialized. So it might be overwriting it. I see. Wait, I think I might know what is happening. Let me check. And not again. I think the problem is happening because the argument pointer is pointing at this temporary segments, and therefore it is overwriting the values of temporary register. Yeah, I was looking for this diagram. This is the RAM. Temp segment starts from this. After that, we have general purpose register and static variables, and this is the stack. So let's see. This is the init code. To run the programs, view emulator, program flow, script. This is the init code. So we get 256. Wait, since the init has been already called, do we need to call sysinit? Yeah, of course, because we have sysinit. We do need to call it, I guess. Let me try to run it again. It will initialize RAM 0 to 61, RAM 1 to 61, RAM 2. Wow, it is initializing the stack to 261, but afterwards we are changing the stack pointer to 256. Is this still incorrect or correct? Let me check. With can be used with VM bootstrap code. This is the bootstrap init code. What did I just do? Continue. I'm going to wait until it changes the RAM5 value. So that we can know. Okay, wait. RAM5 value changed to 123. Wait up. was changed around this point. So at 300 or something. Yeah, over here we are getting 123. Yeah, let's let it run. This is what we should have as the output, 123, right? No, it should contain 120, 135. Was stuck at this point, 174. Let's check where do we have jumps. Okay, we have a jump over here. So maybe we were stuck at this loop. Is it the same thing? Let's see. Yeah, it is at this point that we are stuck. We are stuck at this loop. Where does it come from? Yeah, it might be correct. This is here, loop label. Go to loop. Okay, we'll have to figure out when this value changes. So let's try to run the program. Oh wait, it changed somewhere around here. It changed to 135. Oh, I see. Yeah, wait. After this, where is it? Where did it go? After this push constant 123, we have this call sys add, but we don't have that function over here. Why? Sys dot add. Oh, we don't even have that particular function in this code. Sys This is the VM file. We don't have code for this line. Call sys dot add. Why? Let's check it again. CD Nand2Tetris. Project 7, 8. CD function calls. Nested call. Vim nested dot asm. After push constant 123, how many times do we have this 123? Just once. And 123. We have pop local 3, push constant 1 2 3, and directly we have pop temp. Where's the code for call? Ah, wait. Let me check the code. What is happening? And we have this sys call, sysinit call, and sysmain. Then why don't we have this call? We at least have the code for this function. Where does this come from? Written from a function with Want to swap this fifth window with third window. Swap window is third with fifth. Unknown command, what the heck? Swap window. Okay, so where was I? Wait, where does this comment comes from? Return from a function with no argument. I'm not writing this kind of comment anywhere. Where is it coming from? Return from a function with no arguments. I think we have a bug. See, we are not writing it anywhere. And how am I getting this? Where is this comment coming from? Let me translate the program again. Function calls nested call. What happened? Okay, it is working now. What is this command coming from? I don't get it. Don't even have that comment here. Wow, this function is totally ignored. Where is this coming from? Hmm. What? Why am I getting this HTML as output? Oh, I see. I see. Ah, what the heck is happening? Why is this not responding? Mhm. os dot path dot split text file ext equal to vm get file instance. Yeah, how does it matter, Aditya? Okay, it seems we are getting the correct output now. Let's try to run this program now. CPU emulator, refresh, and load it. What the heck? Let me try to load the script again. all of this code is of return now. Yeah, we still don't have that function label. So why are we not getting that label? Let's check if other functions are working or not. We might have messed up them as well. So let's check. Let's check Fibonacci element. Right. Fibonacci test script. Oh, now this function is not working. What the heck happened? We are going round and round in circles. Before it was working correctly, now this is not even working. Since it is incomplete, where do we have this function main.Fibonacci? Main. Oh, we are calling this function, but it is not even here. Ah, I see. Instead of dot, I have placed a comma over here. Let's try to run it again now. Good, it is working. So now let's get nested call as well. Before that, let's test statics test. Good. Now let's load statics test. tst. What? This was working previously. What happened? Mm. Let's check Fibonacci element again. Okay, this is working. But this isn't working. What? Right. This instruction is getting called, but we are not getting the output. What does that mean? P dot type. Oh, I see. C arithmetic. Wow. Why is it C arithmetic? This instruction is pass C arithmetic. Wow. Why? Let me check. Oh, I see now. It's because of this. So I think we should remove this and it should be the last one. Okay, let's check the program again. Awesome, it is working great. Let's check other programs. Fibonacci element. This one is working correct as well. And let's check the statics. This one is not. It is still giving the same thing. Let's check what is the problem. Why is this program not working? does it check for? Let me see. Statics.test. Designed to set and get various static values. This is done in order to test the handling of static memory segments. This test assumes that the VM translator initializes the VM implementation. Will not begin with. We are taking care of the initializing code. Okay, so I think we have a problem in handling the static memory segment. Static memory segment. Let's check it inside VM emulator. Statics test, statics VM. What is happening? What is it changing? Oh wait, static is a global segment, right? Let's test our own program. This is the state of our program. This is the static segment. Let me check. Starts from 16. Yeah, statics are the basic variables. How are we handling the static variables? Static. Where is the code for static? It is not here. VM logic.py static segment. Yes, this is the code for static segment. Let's compare the static segment. It looks totally different. I see. Is it because of the names? These are incorrect names. I think I know why we have a problem, but before I check it out, let me take a 2-minute break. Static variables should be seen by all methods in a program. Store them in some global space. I have the VM translator. Translate each VM reference static I in a file foo.vm to foo.i. Yeah, so this should be the name of the file. Forget about this. So yeah, I forgot about it. You have to get the name of the file. Where should we get it? When we are reading the files here, we should send the file name as well. How should we send the file name? This file contains the file name. So let's see. File name. Can we have a default argument inside the method? Methods. Let's say the default name. Default is none. So now we can pass the file name here. File. We can use the file name. Let's pass it over here. File name. Right push. File name. And we should use this file name. We need the file name without the extension, so that's what we should pass. 0. Yeah. Well, instead of doing this, let's just get it over here. File name and ext. Let's get this. So now instead of doing this, I can do ext is equal to vm, and over here I can directly pass file name. Now we have to use this file name. Before we use it, let's change the logic. So let's see, we'll do something like this: file and same for the pop. File and right. Let's compile the program again. Let's run this new program inside CPU emulator. We already have it, so let's reset it and let it run. Awesome. So now this program is working correctly as well. So let's try to translate all the programs. Fibonacci element. Let's load it. Running successfully. Now nested call. Nested call.tst. This is running successfully as well. And now statics test. Awesome, this is running as well. Now we can also check the simple function as well. Simple function, but for that we'll have to comment out the init code. So let's do that first. Simple function. Let's load it now. function call, simple function, tst. Great, it is running successfully as well. Let's uncomment this. And with that, we have completely debugged the whole program and we have checked all the programs. It is giving correct results for all the programs. That means our implementation is correct. We might have bugs for the edge cases, but for now this is good enough. So that is it for today, guys. We'll continue with Nand2Tetris again. We'll start working on project 9. Let's check out what is inside project 9 first of all, because that's what we are going to do in the next stream. Higher level language. Oh, it's not that much interesting because we are going to use the Jack language to create this kind of toy programs, so it won't be that much hard, I guess. And this Jack language is like almost similar to Java. Yeah, we'll see it in the next stream. So alright then, this is it for this stream, guys. I'll see you in the next stream. Bye bye.